Okay, class, welcome back. So today we are going to look at chapter 4, which is the finite state machine design, or in short we call it FSM. Yeah. So these are the what we're going to look at in this chapter. So the first one is look at what is finite state machine or FSM. FSM got two types. The first one is more type FSM and the second one is melee type FSM. We will look at both, and we will look at what is called arithmetic state machine or ASM, and also we will look at finite state machine data path or FSMD. Right. So what is exactly finite state machine? So finite state machine is actually one of the sequential circuits that we have learned in the previous chapter, and we also already know that sequential circuit is a circuit in which the output depend on the past behavior of the circuit, and as well as the present state of the input value. All right. And in most cases, clock signal is used. So we know this already. We use the clock signal to control the operation of the sequential circuit, and this kind of circuit is called synchronous sequential circuit. And this synchronous sequential circuit is easy to design, and the most practical and used in many applications. All right, and this is this circuit realized using combinational circuit and one or more flip-flops. We will see later. All right, so we will use what we have learned in the previous chapter, the combinational circuit, and also the sequential circuit, which is the flip-flops, to design the synchronous sequential circuit. All right, and this is the finite state machine. All right, the general view or general structure of the finite state machine is like this, actually. So the output of the flip-flops, we call it the state of the circuit, or the state of the finite state machine. And the name is finite state machine, means that the number of state for this circuit is finite. Machine is simply a circuit. All right. So we will have the combinational circuit before the flip-flops. All right, and this flip-flop give input to the another combinational circuit to give you the output, and this part we call it output logic. All right, and this part we call the next state logic. So the output here we call it the present state. All right, present state signals, and these, all right, will be the next state signals. All right. The circuit has set of primary inputs, W, and produce set of output Z. But sometimes the FSM don't have any input, only clock and reset signal. Or sometimes you may have inputs, one or more inputs to the combinational circuit here. All right, and the stored value in the flip-flop are referred to the state, to refer as the state. All right, so here is the state of the circuit. So of course, under the control of clock signal, the flip-flop change the state as determined by this combinational circuit that fits the input to this flip-flop, and thus the circuit move from one state to another, right, depend on the input here. All right. So in this chapter, we will learn how to use finite state machine to implement practical application to solve real problem, real life problem. So for example, this is a very practical example, design example. All right. So consider an application where the speed of an automatically controlled vehicle has to be regulated as follows. Yeah, the vehicle is designed to run at some predetermined speed. Means that you have a vehicle, and this vehicle is we can say that this is an autonomous vehicle that designed to run at the constant speed. For example, predetermined speed. For example, we want to run at 50 kilometer per hour, right? So we want to make sure that the car will always run at that constant speed, right? But due to some operational condition, the speed may exceed desirable limit, in which case the vehicle has to be slowed down. Right. So for example, if they sometimes maybe going down the hill, right? So the speed is automatically increased. So we want to use our system to automatically control the car so that it's reduce the speed to the desired speed. All right. How to do that? Right. So to do that, the speed is measured at regular intervals. So of course, we need to measure the speed in regular interval, right? So for example, every 30 second, every 15 second, every 1 minute, depend on how you set the specification, right? So let's a binary signal W indicate whether the speed exceed the required limit or not. So such that if W equal to 0 means that the speed is within acceptable range, means that we have one input, all right, to our control system. Now if W is equal to 0 means that the speed is okay, right? But when W equal to 1 indicates that the speed is more than excess the limit already. But in practice, we not just W, all right, equal to 1, we automatically go to or automatically reduce the speed of the vehicle already, because sometimes just that W can be very short only. So we want to look at the W signal that is more than a certain time period, right? So for example, W equal to 1 for more than one clock cycle, 2 clock cycle, 3 clock cycle, then this is the condition that the car speed is more than the desired speed already, so we need to reduce the speed. But if the only W equal to 1 for 1 clock cycle only, and then after that it going down again, so no need to reduce the car speed. So what we want to do is that in this case we want to check if the W signal if equal to 1 during 2 or more consecutive measurement, means that if we measure one time, the speed is equal to 1, yes, more than 1, but we not immediately reduce the car speed. We want to measure the second time, and if the measurement for the second time is confirmed that W still equal to 1, then we reduce the speed. So that's what we want to do. All right. So it will something. It will be something like this. Yeah, where if this is W and this is the output Z, the output Z in this case is the signal to tell the car that you need to slow down your slow down the vehicle, right? Means that Z is the output. So in this case, if we look at W, this is the first measurement, for example, 0. So Z should be 0. All right, there is no action, no need to slow down the car. And for the second measurement, now W go to 1, equal to 1 means that the speed is exceeding the speed limit. So, but we not activate the Z yet, not slow down the car yet. We need to look at the next measurement. If it is go down to 0 already, then nothing happened here. But when it go up again and the next one, we have 1 and Z should be equal to 1. All right. And if we have here 1 1 again, we have 1, another one, we have 1. All right. So if you have 1 1 1 1 1, so Z should be always equal to 1 until W going down to 0 again, then W will be equal to 0. Right. So how to design this? How to create a system that is able to do just this? All right. So with our knowledge before we learn the finite state machine, it looks like it is very quite difficult to design a digital system that can behave like this, all right, using a combinational circuit, for example. All right, because the combinational circuit, we found that whenever the input is changed, the output should immediately change. Means that we cannot actually use the combinational circuit to do this kind of task. So we need to have a sequential circuit where we can look at the previous output, all right, in order to decide the present output or present state of the circuit. All right. So to do that, we can have or we can draw the what we call a state diagram. A state diagram. So in this case, let's draw our own state diagram instead of using this one. So maybe we have this. All right. So in order to do that, we need to have the state diagram. Look at how the state of our system change from one condition to the next condition. All right. So in this case, we can start with the first state. For example, we name this state as state A, and the output for this state, Z, should be equal to 0 at first. Okay. And to go to the next state, for example, we have another state. to go to this state, so we need to look at the input. All right. So when the input is W in this case equal to 0, so we should stay at state A. All right, means that if the speed is still in the limit, all right, under the speed limit, means that W equal to 0, so we should stay at state A, right? And the output Z should be always equal to 0. But when W equal to 1, okay, when we measure the next measurement, W now equal to 1. But remember that if only one measurement, W equal to 1, Z should be, or should stay low. All right. So maybe we have the next state where Z is still equal to 0, but now if W equal to 1, we go to state B, but still now Z is still equal to 0 because only one measurement here, W equal to 1. All right. And if only in the next measurement W equal to 1, then we have Z equal to 1 here. All right. So if W equal to 0, so we stay here, nothing happened, 0, 0, 0. But if W equal to 1, we need to go to this state and we wait for the next measurement. If W still equal to 1 for the next measurement, so now Z should be equal to 1. But if in this case, this state, if the next measurement W equal to 0, where we should go? Whether we stay in this state or we go back to A or go to another state. All right, it depends on how we design. So in this case, it looks like if the next measurement, if W equal to 0, we should go back. Right? Because why? Because if 0, we need to wait for the next 1 and 1 in order to get Z equal to 1. So for example, if we have the input 0, 1, now 0, we need to look at the next one, 1, in order to get Z equal to 1. All right. So in this case, if for example 0 now, 1, which is this one, 1, and now the next one is 0, so we go back and wait for the next one. Next one, W equal to 1 and 1. Now we have Z equal to 1 here. All right. If not, you need to go back. All right. So for this one, if W equal to 1, we go this. If W equal to 0, we go back to A. All right. So it should be done for this state. Only this. The last state. If we in C, if the next one is equal to 1, so the Z should be always equal to 1, right? Until you have 0, then Z should be 0. So means that if W equal to 1, we should stay here, remain at C, so that Z will be always equal to 1. If not equal to 0, we need to go to other state, maybe state D, or maybe go back to A, or maybe go back to B. So if we go back to B, if we go back to B, if W equal to 0, what if the next one equal to 1? Like this. So if next one equal to 1, we need to go back to C, means that Z equal to 1 already. Alright? Which is wrong. So we cannot go back to B in this case. Alright? So maybe we go back to A, or go to other state, D maybe. Right? But this case, let's go back to A, so that, for example, we have the next one 0, and the next one come 1. 1 here will bring us to B, and if another one come, we go to C, and yes, of course, Z equal to 1. Right? So this may be the right state diagram for us, right, in order to implement that application. Okay, any question for this? So this one we call state diagram. Okay, so if no question, we will design the circuit to implement these in the hardware, right? How do we design? So the first thing we need to do is we need to represent this behavior in digital. All right, so we can have something like this. We call it a state table, right? So what is state table? So we need to represent this diagram in the form of table, right? So maybe I have something like this, so that I can draw the table. Okay. Okay, I can have something like this one. We call it present state, where we have state A, we have state B, we have state C, and then we have the next state, and then we have the output. So next state, we have two possible conditions. Where the first condition is where W equal to 0 and W equal to 1. Alright. So if we are in state A, the present state is A, if W equal to 0, where should we go? We should remain at A, right? And if W equal to 1, we should go to B. So we have B. And the output at state A should be Z. So output is Z, should be equal to 0 in this case. And at state B, when we are at B, so when W equal to 0, we should go back to A. So we write A here. And if W equal to 1, we should go to C. And the output at B, Z should be equal to 0. And the last one, Last one, state C. So when W equal to 0, we go back to A. And if W equal to 1, we should remain at C, and the output at C is equal to 1. Or you cannot see that. Okay, there. Here you go. Right? Hope you can see this. Okay, so this is the state diagram for this one. So let's see. Yes.
And the slide before this. Why at the when the W is 0 but the Z is equal to 1? Slide.
Yeah. Oh, hold on. Okay. We'll check. Yeah. Okay, should be better. In the slide.
Yeah.
Hold on. Wait, I open the slide. Is it different from this?
No. Before this slide.
Before this slide. Here.
Yeah. At T9 when W is equal to 0, Y Z is equal to 1.
Oh, okay. You change. That one is need to update the slide. The latest one is this.
Oh, okay.
The latest one is this. We have T7. Okay, sorry for that. So this is the latest one. Can you see the here?
Okay.
Yeah, it's means that the I show you the previous one. The previous one is 1 cycle delay. Yeah, the output.
Yes.
And this one is the update one.
Oh,
okay. So for example, we have here 1 1 1 1. So Z should be equal to 1, and 1 1 here, Z here should be equal to 1, and when still 1, so Z is still 1 until you have T9 equal to 0, then it will go down to 0. Yes, this one, yeah. I think in your notes, you get this one or the wrong one. Okay, I will share the new one after our class. Yeah.
Okay, thank you.
Okay, thank you. Now let's go back to this. All right. Okay, so we have this. Now this one cannot be represented in digital yet. All right, so we need to change this A to digital representation first. All right, so the state A we need to represent in digital. So what is state A actually? So state A is actually this, yeah. Okay, so if we look back to the general structure of the finite state machine, we have something like this. So the state, whether it's A or B, is actually the output of the flip-flops. All right, the output of the flip-flop. So the output of the flip-flop, if you have one flip-flop, so can be 0 or 1. If you have two flip-flop, it can be 0 0, 0 1, 1 0, and 1 1. If you have three flip-flop, it can be 0 0 0, 0 0 1 until 1 1 1. All right. So that is actually the state. The state. This is the output of the flip-flops. Okay. So in this case, back to this. Alright, meaning that A and B and C are the output of the flip-flop. Alright, now we have three possible output. Alright, so we need how many flip-flop to represent these three possible output? So you should have at least two flip-flop, right? If you have one flip-flop, you can only represent A and B. You cannot represent C, because maybe you represent A as 0 and B as 1. What about C? Cannot. So you need to use two flip-flops, so that you can use 0 0, 0 1, 1 0, and 1 1. Alright, in this case you can represent up to 1 0, which is C. So you can represent A as 0 0, B as 0 1, and C as 1 0. So instead of using A, B, C, now we have a digital value for A, B, and C. So we can have now something like this. Instead of using A, B, C, so now we need to represent this with this. A, now we change to 0 0. B, we change to 0 1. C, we change to 1 0. And you should have another one, which is 1 1. You should have as well. Alright, because digital number, you need to have every possible combination. And if W equal to 0, remember we still at A. If W equal to 1, we go to B, which is 0 1. And if at B, or 0 1 in this case, when W equal to 0, we go back to A. If W equal to 1, we go to C, right? 1 0. And at C, when W equal to 0, we go to A. And when W equal to 1, we go back to, we stay at C, remain at C. And here we don't care, so we put D. D represent don't care, and the output is 0 0 1, and you have don't care there. Alright, so this is the what we call the state assigned table. Okay, where we assign the digital value to the state instead of using A, B, C. Right? Now, what we want to do is that we want to design the circuit for this. So to do that, we need to have our block diagram of our circuit. Right? Remember, we have two flip-flop now. We'll have two flip-flop. So you have two flip-flop like this, and you will have what is called the what we call a next state logic. Here, where the next state logic is depend on the input W, and this is D, this is Q, this is D, this is Q. All right, and you will have the another one is the output logic, where the output of this flip-flop, which is a state, present state, will drive the output logic and give you signal Z. And of course, you need to have the feedback signal here. Go back to this and this. Right? So you will have something like this. Is like just like this. Just like this. Forget about this purple color signal. So this will represent the milli type state machine. What we do now is the mod type. So we have, remember, we have more FSM and milli FSM. So for more SFN, we don't have this signal. All right, forget about this. We only have this feedback. From this, go to the next state logic. All right, just like what we have here. Yeah, this is the, we have W, we have next state logic, we have this flip-flop, and we have Z, and we have the feedback. So this is the general structure, and we want to do this, and we want now we want to generate this signal. All right, and Z. Okay, so how to generate what is inside the next state logic? Of course, this is the combinational logic, and this also will be the combinational logic. So let's label this signal as Y. In this case, I give it Y1, capital Y1. This is capital Y2. This is small y1. I don't want to use y2. y0. And this is small y1. This is small y0. In the notes, in the note is in the notes is y1 and y2. Change to y0 because y1, y2 when you do code in a Verilog, you will have a problem. So change to y1, y0. Okay. So in this example, I use y1 and y0. Okay. So we want to get this signal, right? The output. What? So y1 will be the signal that will depend on what? These two signals, right? y1, small y0, and w. y0 also will depend on these three signals, alright? But z will depend on these two. Okay, so we need to get the equation for y1, y0. Okay, so now what is y1, y0 actually? So this is actually this, because this is a present state, right? This is the next state. All right, next state. So this is present state. So this should be y1, y0, and this one is next state. So this should be y1, y0, and this is y1, y0. Right? So these are actually y1 and these are actually y0 for if w equal to 0 and if w equal to 1. This is y1 and this is y0, right? So that is the signal that we need to have. So if we have this and we have this already, we can derive the Boolean equation for the this. So how to do that? So you can have, for example, you want to derive y1 first, yeah. So you can have the truth table. So the truth table. So you can have something like this, right? Here you have y1, y0, and here you have w, and y1, y0, you have 4 possibilities. So you can have 0, 0, you have 0, 1, you have 1, 1, and 1, 0. This is how we arrange the signal in K-map. Remember, you learned this already. So you have w equal to 0 and you have w equal to 1. And when we look at this, yeah, for y1, look at this. So y1 will, if w equal to 0, y1, if 1, 1, y0 equal to 1, y small y1, small y0 equal to 1, 1, and w equal to 0, so you have d. So 1, 1, where is 1, 1, and here you have d. Alright, and for w equal to 1, you have y1, 1, 1, d. Alright, 0, 1, 0, 1, you have 1, 1, 0, you have 1, 1, 0 here, you have 1, and for 1, 1, 1, you have d. Alright, so you have something like this. The rest should be 0. And you can have the equation from this, where you can map like this. And another one is this, right? So the first term will be w y0, or the second one, which is w y1. So this should be y capital Y1 should be this, and you can simplify this by factoring w. So you have y0 plus y1. Yeah, you have the equation for y1. So you can have this one already, where the relationship is that you have an AND gate here and the OR gate. And what about y0? Okay, so for y0, you can have the same truth table. Right, maybe I copy this. Okay, for y for y0, so we will look at y0. So y0, if w equal to 0 and y1, y0, we have 1, 1, 0, 1, 1, you have d, don't care. So you have don't care here. And what about this? you have 1 here, 0, 0, and w1, w equal to 1, 0, 0, w equal to 1, you have 1 here, and you have d here, 1, 1, 1, 1, 1, 1, d. So because this one is don't care, yes, we don't care this, we just care about this. Okay, so y0 we can have equal to w, this one is y1 for y0 for, so that will be w. What about z, the output? So we want to design this, what is in here, z, so it will depend on y1 and y2, y1 and y0 only. So z is depend on this only. Very straightforward actually. We can observe that z is because this is don't care, we can say that this is equal to 1 or 0. So in this case, if we set this equal to 1, so we can say that z is actually equal to y1, right? 0, 0, 1, 1, 0, 0, 1, 1. So z, we can say that z is equal to y1, or maybe you can have your k-map, right? You can get the same value where z is equal to y1. So now you have all the equation already. Now you can design your where is it? Okay, your finite state machine. All right, where the circuit is something like this. All right, just change this to y0 and y1. Yeah? All right. So this is the circuit that will give you this this behavior. All right. So it looks complicated. All right, because you have only 3 states, 3 state, and the process is quite long. You need to design the state table, and you need to design the k-map to get the Boolean equation, and of course from the Boolean equation, because you have the Boolean equation, now you can write your Verilog code. But the good thing is that in Verilog we can skip this process, I mean this very long process where you need to get the equation. Because why? Because just imagine if you have 5 states or you have 10 states or more than that. Just imagine how you want to design this. There's state table, state assign table, state table, k-map, and of course the equation, which is too difficult, right? Quite difficult for us. But the good news is that we can use behavioral modeling to describe our finite state machine. Means that we can skip this process, but we just use this state diagram to create or to describe our circuit. All right, meaning that when we have the state diagram, we can straightforward write the code. All right, so how to do that? Okay, so to do that, we need to, maybe I show you in quarters. So let's open the quarters too. Okay. right? So, and because we have something like this, we have learned already. If we know the relation between W and this y, small y1, y0, we can produce capital Y1 and Y0, right? And also, if we know when Z will equal to 1, depend on these two signals, then we can write the code for that using behavioral modeling, right, in Verilog. So let's look at the quarters 2, right, to write the code for this one. Actually, what we want to do is this code for this, actually, for this one. So again, write the code, and of course the state. Right, to do that, so we need to create a new project. You can do this very fast. So we have Finite state machine. Maybe we have example 1. Okay. Let's name this as FSM1 more type. More. We can finish this and we can create the new module, more types. So what are our port list? So we can look at this. Of course, we have the clock and the reset. So we have clock and we have reset, name it at CLK and RST. And we have what? We have W and we have Z, right? Our input is, we can just copy this, and we have output, and of course in the form of rect data type set. And now we need to describe this. Okay, y1, these two signal, all right, y1, y0, small y1, y0, capital y1, y0. So this should be in rect, and we have 2, we have 1, 2, 0, and we have y, right, small y and big Y here for these two. And we want to represent the state as a name, for example, in state A, state B, and state C. So we can use parameter declaration, and the size is 2-bit. All right, same as this one. Okay, state A, so is represent 2-bit number. 0, 0 is state A, and we can have B is 0, 1, and you can have the last one. C is 1, 0, right? So A means state A, and it is represented by 0, 0, and 0, 1 is for B, 1, 0 is for C. Okay, and now we want to define this. All right, the flip-flops, yeah, or this we can call it register because we have two flip-flops. We name it as state register. Okay, so to define that flip-flop is easy, so we can use always, and of course post-age clock for safe age, and we have for safe age reset. So if reset signal equal to 1, so what happened to this? The output for this should be equal to 0, or we should go go to state A, right? 0, 0 means state A. 0, 0 means that if we reset, yeah, we should go at we should stay at state A. Right, so this we can write like this: if reset y should be equal to A, or A is assigned to y, which is 0, 0, yeah, state A. And if not reset, the output of y should be what? Should be capital Y, right? Here, capital Y. So we should have y. So now we have this flip-flop already, or the state register, we call that. And now we want to define the output Z and also this. So this, we know that it is depend on this two, and also W, and this will depend on this two. So we can use behavioral modeling. Again, you can use always block, and in this case we want to define or describe the combinational circuit. So we need to use, or we need to have the what we call the sensitivity list. So what should be in the sensitivity list should be W, because this will depend on W, and also Y1 and Y0. So it should be W and W or Y. Okay, and we want to define this and also this, so we can combine already. So we can name this as output and next state logic. All right, so we can use case statement, case Y. Okay, case Y. So Y, yeah, if Y equal to 0, 0, or at state A in this case, yeah, so Z should be equal to, yeah, back to this, if 0, 0, so Z should be equal to 0. Okay, and if 0, 0 also A, we need to depend on W signal. If W equal to 0, we should stay at A, And if W equal to 1, we should go to B. So we have two statements there. One if, so we need to have begin, right? If A, so Z should be equal to 0, right? And if W equal to 1, what do we do? W equal to 1, the next state, next state here, if W equal to 1, here, we should go to B, right? So Y here, capital Y here should be equal to B. Else, Y should be equal to A. Means that if W equal to 1, we should go to B. If W equal to 1, we should go to B. But if W equal to 0, we should stay at A here. Okay? So we can end here. So here we define the state, state A, right? We depend on this behavior. And we have B. If we are at B, again we have begin, and B, Z should be equal to 0. Here, 0. And if W, we should go to state C. Else, we should go to A. Done for B. And the last one, C. Z should be equal to 1. And if W, what we do? What do we do? Y should be equal to C, right? Stay here. Else, Y should be go to A, go back to A, and should be done. And remember, you have another one, which is 1 1. Don't care one. This one. Don't care. So this one is not D or whatever. So we can say that this is other than this. We can say that default. Yeah. We can have begin. We need to define also. Z we don't care here. We can say that Z should be equal to 1 bit. Don't care is X in Verilog. And Y, don't care also, but Y is 2 bit. And done. Now we define all the possibilities already. So we have n case here, and done. Okay. So it should be all of this to represent this behavior, right? So let's save this. Save, and then try to synthesize this. Got error. So what is the error? So if you have error like this, don't panic, yeah. So read very careful what is the error. It will tell you, the software, the quarters will tell you what is the error. So here you can double click, so you don't have semicolon here. So forgot to do that. I think nothing more. Alright, and this is due to the previous error, so it should be no problem now. Alright, there is one warning, and of course this warning is about the license. Should be no problem with the design. And now we want to simulate this, and to simulate this you need to write the Testbench. So the Testbench, I will use the previous Testbench which I have already. So maybe just copy this and paste, right? Except that the name for this one should be, because we want to instantiate this module to here, so the name must be the same, FSN1 MOORE, more, and the name is yeah, that's. So this is the Testbench, and we will see if this is the input of W, and we will see what will happen to Z. Yeah, okay, so let's save this as this. Save, and we try to run this. Remember, you need to go to setting and make sure that you select this, and you want to compile the Testbench. Create a new one. The name is this, and you need to add the file. Should be FSM 1 TB, open, add, okay, click OK and click OK here. Set already, then you run. Okay, wait for a while. So this is the result, and you have this. You can see here, this is W, and this is the clock that represent the measurement, measurement interval. So one clock cycle means that one measurement, right? So for example, in this measurement, W go to 1, and we see that after one clock cycle, another measurement, the W here is go down to 0 already, so Z will never go to high, yeah? Right? So in other words, no need to reduce the speed of the vehicles, right? Because it's only exceeding one measurement, exceeding the speed limit in one measurement, and the next measurement is going down already, so should be no problem. And here also the speed is going up because W is equal to 1, and again only one measurement, so Z remain 0. But here we see that for the two consecutive measurement, the first one and the second one, we see that the speed is still exceeding the limit. So now Z is equal to 1 already, and the third measurement still 1, yeah. So if we have 1 until W go down to 0, then you go down to 0 here, right? So this is how the FSM is designed and simulate, yeah, in quarters. Okay. All right. So any question? So we are at 12:07 already. So we should stop our class here. And what you can see is that here with Verilog, yeah, we can skip these troublesome step where you need to design the circuit using K-map, derive the equation before you get the circuit like this, yeah. But by using Verilog, you can straight away describe the finite state machine using its behavior. All right. So whenever you have the state diagram, you can straight away write the code based on the behavior. For example, you describe the flip-flop here, right? Very easily can be described using Verilog. And to get y1, y0 here, we can use the behavioral modeling here. For example, in state A, all right, z should be equal to 0. And what is about the signal? The signal, if w equal to 1, so we should go next is go to B. But if w equal to 0, we should remain at A. All right. But if we are in state B, when we are the output should be 0, right? Clearly based on this state diagram. And if y equal to c, if w equal to 1, so we go to state C. And if w equal to 0, we go back to state A. And for the last one, when we are in state C, if z should be equal to 1, if w equal to 1, so we should remain at state C. And if w equal to 0, we should go back to A. Go back to A, and again, because we use case statement here, case statement, so you should have all of the possible combinations of y. So in this case, you have y equal to 0, 0, 0, 1, 1, 0, and 1, 1 actually. So we don't care that value of z and y, so you can write like this, and done. And you can simulate and get the result, right? So if the result is not correct, means that some of the design here is not correct. So you should go back and check what is going wrong here. Okay, so that will be the lecture today. Thank you very much.